diving into something pretty fascinating. Hey, it's great to have you here for this episode. Today, we're diving into something pretty fascinating: input output analysis. It's this economic tool developed by Wassily Leontief back in the 1930s and 50s, and it actually earned him a Nobel Prize.
Yeah, it's really interesting stuff. Basically, it helps us understand how different industries in an economy depend on each other. Kind of like a giant web where every strand connects to another. If one industry changes, it ripples through the whole system.
Exactly. Think of the economy as a big recipe. Each ingredient, like steel, labor, or energy, depends on others to make the final dish. Input output analysis puts numbers to those relationships, showing how much one industry needs from another to produce its goods.
Right, and it does this using tables or matrices that map out the flow of goods and services between sectors. So you can see who's buying from whom and how industries are linked.
Now, there are two main types of these models: closed and open. The closed model is like a self-contained factory, where everything produced is used internally by the industries themselves. No outside consumers.
Uh-huh. Whereas the open model is more realistic because it includes final demand from outside sectors, like households or the government. So it accounts for both intermediate demand, industry to industry, and final demand, which is goods consumed by people or exported.
That's a key point. The open model also includes inputs like labor, which industries don't produce themselves but need to operate, so it captures a fuller picture of the economy.
Speaking of capturing the economy, the Leontief model is central here. It uses a matrix that shows how much input from each industry is needed to produce one unit of output in another. The core equation is something like times x equals y.
Yeah, where A is the matrix of input coefficients. Basically, fixed numbers showing how much input per output unit is needed. X is the total output, and Y is the final demand. The model assumes these coefficients are fixed, meaning the input proportions don't change over time.
And the magic happens with the Leontief inverse matrix, which helps calculate the total output needed to satisfy final demand, including all the indirect effects. So if demand for cars goes up, the model tells you how much steel, rubber, and labor are needed across industries.
That's really powerful for policymakers. It helps them see the ripple effects of changes in one sector on the entire economy. Like, if the government increases spending or a new technology is introduced, they can estimate impacts on employment, income, and production.
Plus, it's useful for spotting bottlenecks or vulnerabilities in supply chains. And interestingly, it's been used in Marxist economics for planning, as well as in modern environmental and social impact assessments.
Speaking of different uses, there are several types of input-output models. The static model is the original one, assuming fixed production coefficients, a snapshot in time.
Then there's the dynamic model, which allows those coefficients to change over time, capturing things like technological progress or shifts in consumer preferences.
We also have regional models that focus on economic interactions within a specific area, like a city or state, and multi-regional models that study trade and economic links between multiple regions or countries.
Don't forget the environmental model, which adds factors like resource use and emissions, helping to plan for sustainable development.
And the social and inter-industry model, which looks at employment, wages, and income distribution across sectors, showing how economic activities impact social outcomes.
Now, the model has some key features. The transaction matrix is the heart of it, showing who buys from whom and who sells to whom.
It also distinguishes between production flows, inputs used by industries, and consumption flows, which are final goods sold to consumers.
And it highlights sectoral interdependencies, showing how a change in one sector affects others, which is crucial for understanding economic resilience.
The multiplier effects are another big deal. They explain how an initial change in demand can have amplified impacts across the economy.
Right, and economic impact analysis uses these models to simulate scenarios, helping policymakers weigh benefits and trade-offs of different decisions.
But, of course, the model has assumptions we need to keep in mind. It assumes fixed coefficients, meaning input proportions don't change, which isn't always realistic.
It also assumes linear relationships, so changes in output demand lead to proportional changes in inputs, which can oversimplify real-world complexities like economies of scale.
Plus, it assumes aggregate demand equals supply, meaning the economy is always in equilibrium, which doesn't capture recessions or excess capacity.
And it treats goods within each sector as homogeneous, ignoring product diversity, which can be important.
Another assumption is time invariance. The structure of the economy stays stable over the short to medium term, which misses longer term changes.
There are also limitations like no price adjustment mechanism, so it doesn't show how prices respond to supply and demand changes.
And it focuses mainly on production, not explaining why input-output patterns exist or how final demand might change in response.
Still, despite these limitations, input-output analysis remains a foundational tool. It helps governments and businesses plan better by revealing how sectors depend on each other.
Especially today, with global supply chains and environmental concerns, understanding these interconnections is more important than ever.
So thinking of the economy as a living network where every part affects the whole really helps make sense of complex economic dynamics.
Absolutely. That's a great way to wrap it up. Thanks for exploring this with me.
Thanks. It's been a pleasure.